So we're looking at moment of inertia of a solid sphere. So we have a sphere and it's rotating in this manner. Actually, it could have been up straight also. I still can do it in up straight form. So I'll try doing this in up straight form. Not very happy with that. So we have a disk. Let me just take a second. Okay, yes, this is what I meant. So we have a sphere that is rotating in this manner, up straight. And yeah, so basically, no, let me show the animation later. So we're going to make use of, yes, I is equal to R square dm. Now, for integration, we need to do a bit of circus. So for above integration, it will be convenient to divide the sphere into thin slice of disks with dx width placed perpendicular to the diameter AP. Okay, so basically what we're doing is we are considering this thin disk. So this happens to be, oh, just a second, I just need to change few things. This happens to be of width dx. Okay, so actually I need that space. Let me write it over here. This is of width dx. So we are dividing many such. So obviously what is that we're looking at? The disk size will not be the same, right? If I take some disk over here, take one more disk over there, take one more disk over here, it won't be uniform. So what I mean is, if we keep slicing that way, it would look something like this. You guys agree? So there'll be many of them, and if they rotate, it would look something like this. Can you see that it's rotating? You see that it's rotating? So imagine that they are made up of many such disks. Obviously, a sphere will be made up of many such disks. Very thin disk, you can imagine that. And they form a sphere, basically. Okay, so that's what we are assuming. That's what we're starting off with. Okay, so such disk, the width is dx. And of course, there is a lot of things that we need to work over here. It will be a bit off than what we have done till now. So the sphere radius is r, right? That is not visible. So this is radius of r, and yeah. So we need to consider one such disk at a distance of x from O. So this is our O. So this is x. This is x. This length is from here till say here. That's x. Right, guys? So basically, we are looking at a disk rotating. So we saw here, right? We're basically looking at a bunch of disks rotating. Now, so we'll start off with what we know. We know that your moment of inertia of any disk rotating around its center. Let me actually write the statement. Moment of inertia of disk rotating along its center perpendicular to plane. So by now you guys need to know this formula. I of disk is equal to half of mass of the disk times the radius. Now, the mass of this disk and the radius is what the tricky part is, So mass of each of the disk and the radius is a bit tricky because the radius clearly they are not the same. Where is it? They're not the same. But we need to make it as a function of one single variable. And that variable has to be x. So let's see how to do that. Now, mass over here, mass of such a disk would be density times volume. Okay. So that's, since we are dealing with 3-dimension and a lot of variation, so we'll just go with density times of volume. So density is given by the entire mass divided by the volume of the entire sphere times now the volume of a disk. Volume of the disk, how do you find it? It's a circle. So we have pi r square radius square times the thickness. Thickness is dx. Okay, circle times the thickness will give us the cylinder. Basically, indirectly, we are looking at here, just a second. Here we are looking at a cylinder. This is a cylinder formula, technically. So we have pi and pi getting cancelled, and radius. So the radius, you can see that radius will not be the same for all of them. Radius will be different. So how do you handle it? So radius has to be expressed in terms of x and r. So radius will be r square minus x square root. So this is as per your Pythagorean theorem. So we have this to be, okay, I'll just write it over here. 3 by 4 m by r cube times r square minus x square dx. Okay, so that would be your mass. Then I of disk will be, guys, it's radius times radius. Actually, it will be square of this. So I'm going to square it. Don't get confused, because there is one more radius over here. Radius times of radius will be radius, this is radius square. My bad. 1 by 2 mass times of radius square. It's always square. Okay, my bad. So this would be times of r square minus x square, the whole square dx. Okay, so we have the basic formula now. And now we'll move on to of the sphere, which will be integrating from one end of the radius to the other end. Okay, so let me show this. So one end of the radius to the other end. So minus r to r. So this will be your minus r. That will be your r. So we are integrating from minus r to r, the value of I disk. Okay. So I'm not going to write the limits again and again over here. Please see to that you guys write it. So we have, oh, sorry, I missed out half over here. This will be 3 by 8. There's half also now. I should have done it systematically, the substitution. I should have not done this. 3 by 8 mr cube. There's simple, straightforward, constant values. Integration. So here we have x squared, so we can't take it out. We need to expand this. There's no other option. So 4 minus 2 r square x square and dx. So remember, it's minus r to r. I'm not showing that. And integration of this, I'll just write it over here. 3 by 8 m by r cube, brackets open, r to the power of 5 by 5. Oh, sorry. we are integrating with respect to x now, r to the power 4 x plus x to the power of 5 divided by 5 minus 2 by 3 r square x cube, and the limit will vary from minus r to r. So all these are odd functions, they will add up. If it was square functions, it would have even functions, it would have cancelled, but we have odd functions over here. I hope you guys know about quite a few properties from integration. I'm actually skipping out few of the shortcuts so that I don't confuse you guys. So this will end up with 2 r to the power of 5. Then this will end with 2 by 5 r to the power of 5. And this will end up with, this also will be 4 by 3 r to the power of 5. It has to be so actually. Okay, finally we have a bit of calculation over here actually. So let me add them up. 2 plus 2 by 5 minus 4 by 3. 16 by 5. 3 by 8 times of 16 by 15, my bad, into r m by r cube into r to the power of 5. So this n square, and 1s are 5s are, 1s are 2s are. So we have 2 by 5 m r square. Okay, so that's that. Again, always take it systematic. Always understand what kind of... Sorry, I could have made the animation for others also. I don't know. I just missed it. I just think this was complicated. So I thought for this I had to make. For others also I could have made actually. I don't know. I missed it. So anyways, I'll try to fit in when needed, as and when needed. Okay. So you can pause, have a look. Always imagine, sorry, I went to that to tell you guys that always understand what kind of subdivision you are making, and how is that basic formula, and how you can relate it to the main thing, and how the variables are, and how we are integrating. Same way, everything follows the same structure. This was a bit off, but yeah, such questions will be common in the future. Questions derivations will be common in the future, wherein you are expressing a complicated scenario with a single variable. Okay, so get used to it. So please see to that. You pause, have a look.